So what is the gradient of a tangent? A gradient of a tangent is the gradient of a curve at point of contact where it just touches the curve. Let's see what I mean. So if I have y equals to x squared like this, and I draw a tangent is a line that just touches the curve. So it doesn't cross it, it just touches it. So the gradient of the curve at this point here is the gradient of the tangent at this point. And obviously the gradient of the tangent is a straight line, change in y over change in x. So that's the gradient of a straight line. Change in y over change in x. Now, this video, we're talking about from first principles. And what do we mean by this? How do we derive the gradient of any function? So this is how you would do it. So if there was ever a function that you did not know the shortcut of how to find its gradient at a certain point, you would use first principles to get to the derivative or the gradient of that function. So let us use an example. So at the moment we've been using y equals to x squared. So we'll keep that. How do we do it from first principles? And by the way, Oxbridge loves asking questions and they love using from first principles. In fact, your first year, second year, everything is taught really from first principles. So it's a good skill to have because it helps you solve problems that you have never encountered before. So let's have a look at this. So here we have y equals to x squared, or f of x equals to x squared. Okay, now in order to find what the gradient is, so if you look at this y equals to x squared graph, right, and we're looking at this point here, let us call this point A, and we draw this tangent here. You can find the gradient of this line, obviously, as we said, by taking change in y over change in x. So obviously, to be able to do a change, you need 2 points. So let us call a point B elsewhere, whereby we can say, let's say point B is here. So change in y, change in x is the gradient. So point A is a general point xy on this y equals to x squared graph. This is x and this is y. But point B is x plus h. So B is just h distance away from A, right? So it says x plus h is the x coordinate of point B. And it also has a point y. But obviously, because the function is f of x equals to x squared, if x is now x plus h, the value of y at that point is x plus h squared. So in fact, point B is x plus h squared. Now remember, this is not always the case. This is just the case because f of x in this example is x squared. But as I said, you can do this for any function, and I will show you how to generalize it even further. At the moment, we're just looking at x squared. So change in y over change in x equals to, well, point B. This is the y value of point B, which is x plus h squared. Take away from y here, which is just x squared, all over. This is the point x for point B, so it's x plus h. Take away point A is just an x, right? So this is x plus h squared minus x squared over x plus h minus x is just h. And in fact, you can expand this into x squared plus 2xh plus h squared minus x squared over h. And therefore, change in y over change in x is 2xh plus h squared over h. And in fact, if I cancel here and here and here, this is 2x plus h. So this is when we start talking about differentiation, because this is a gradient. This delta here is a large change. Now, when we start considering h being very small, think about what happens in this graph here. If h is very small, point A and point B are so close together. This is when we introduce limits. So in the limit that h tends to 0, it becomes very small, such that point A and point B are so close that you can say that they are the same point. The change in y over change in x, the change in y over change in x, so this is when we talk about the small change of, the small change in y over the small change in x. What happens here? 2x plus h. H becomes very small. This becomes 2x. Right? It tends to 2x. So let us talk about a few definitions here. When we're doing limits, right? When we say the limit as h tends to 0, or here it's actually supposed to be delta x, because delta x is what is becoming really, really small in this example here. Otherwise, yeah, here the limit is, yes, like that. It's delta x tends to 0. So here delta x tends to 0, it becomes 2x. When we talk about limits, in the limit that delta x tends to 0, change in y, the small change in y over the small change in x becomes dy over dx. So you do not need to write this anymore, because these are equal. This is in fact the definition notation. Okay, so dy by dx of y equals to x squared equals to 2x. What does this mean? It means that the gradient is 2x. So at a point where, for example, here, where it is 0, 0, dy by dx at x equals to 0 of this y equals to x squared function, it's 2 times 0, which is 0. And it is true, because if I draw a tangent here, it's just a straight horizontal line that has a gradient of 0. So that is how you get there. So yeah, so we know that dy by dx of f of x in this situation is 2x. So how do we make this more general? So by more general, I mean y equals to just an f of x function. So solving from first principles, and we have a function, could be anyhow, and again I can draw a tangent, point A to point B. This is a change in y, this is a change in x. The function is f of x. So what happens in this situation? Well, at point A, this is x, y, right? But y is just an f of x function. So point A is just x and an f of x function. The value that you get when you put x into f of x is what is the value of y. Point B is x plus h plus y of point B, which is x plus h, f of x plus h, right? So change in y over change in x is f of x plus h minus f of x itself all over x plus h minus x. So this take away this, and this take away this. Okay, so the limit as h tends to 0, or this is, h is actually dx, so h is signified by this distance here. It is h, it's called, well, here I called it delta x, capital delta x, as a large difference, but we could be talking about a very small difference as well, but also h as a difference is also noted as h as a difference in other cases. It just depends with what term you want to use. Okay, so the limit as x becomes very small, or h becomes very small, of this small change. This is just to denote small change, as opposed to here where it's a large change, like in a straight line. In a curve, we usually use this delta to signify a small change. Of the small change in y over a small change in x equals to f of x plus h minus f of x over delta x. Now, this is the definition. This is what differentiation means. This is what you do when you're differentiating. And it has various notations, right? So you can say dy by dx, or you can write it f dash x. So this dash means the first derivative. After you differentiate once. Okay, so in the spirit of being more general, can you please find from first principles what the differentiation is of f of x equals to x to the power of n? So this is any polynomial. So n can be any number, okay? So tell me in this situation what you will find. Well, let us do it. I'll do it in a different color, just to note that this is a question that you can go and do by yourself, and then come back. You can pause your video here and come back and say what you got. So again, I can just draw any curve anyhow. This is x to the power of n. This is point x, so this is point y, and y is x to the power of n. And then I've got a point B here, and the point B is x plus h away, and therefore the y equivalent is x plus h to the power of n. Okay, so when I'm doing change in y over change in x, what do I have? I have change in y is x plus h to the power of n minus x to the power of n all over x plus h minus x. Okay, now the numerator demands some expansion, and we have done this in the previous video, which I will link here, where we talked about combinations, we talked about the binomial triangle, how to expand polynomials, what are the terms and the coefficient, and number of ways of choosing something. So just go and watch that video so that you know how to expand this. But essentially, x plus h to the power of n, how is that expanded? Well, if you look at the terms in the polynomial, remember we have in the binomial, in the Pascal's triangle, remember n choose r, right? So here we can just write this as, remember we had a plus b in that video to the power of n equals to n choose 0, a to the power of n, b to the power of 0, plus n, a, n minus 1, b to the power of 1. Why is it n? Because n is n choose 1, right? N choose 1 is just n plus n choose 2, a, n minus 2, b 2, plus dot 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 to the end of it. So in a more general term, a plus b to the power of n equals to n choose r, a to the power of n minus r, b to the power of r. The sum over from r is 0, all the way to r is n. Okay, I didn't have to remember this formula. I just had to remember the Pascal's triangle or the binomial coefficients and how to write them. Just one line of the triangle, and therefore I can generalize it like this. So coming back to the x plus h that we have here. So we have, I'll just highlight this as it's a separate thing, right? So we have x plus h. How do we write this? Well, small change in y over small change in x equals to x plus h. H is a small change minus xn over h. This equals to the sum over from r equals to 0 up to n of n, choose r, x, n minus r, hr minus x to the power n all over h. Now, if you expand this, the first few terms, the n choose 0, x to the power of n, h to the power of 0, plus n choose 1, x n minus 1, h to the power of 1, plus n choose 2, x n minus 2, h to the power of 2, plus dot dot dot. This is this term here. I just expanded the first 3 terms minus xn, and the reason I only did that is because I have to subtract x to the power of n, and I just want to see where it's coming, where I'm going to subtract it from, all over h. Okay, now you see n choose 0 is 1, x to the power of n, h to the power of 0 is also 1. So this is x to the power of n plus n choose 1, remember we said that's n, x to the power of n minus 1, h to the power of 1 is just h. And then we've got plus n choose 2. Now obviously that depends what n is, or in fact, I'm just going to leave it like this for a second because I need the space. H to the power of 2 plus dot dot dot. Now minus x to the power of n out of a h. This goes from here. Okay, leaving me with n x n minus 1 h plus n c2 x n minus 2 h2 plus dot 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 all over h. Now when you're doing this, you can see that h will cancel with this h, it will cancel with part of h here and part of h here, etc, etc. So the only term that won't have the h is the first term or the second term previously. So how can you rewrite that? Right? How can you rewrite that? So when I go back to writing it as a sum, where I had it here, as a sum here, it is a sum over n choose r, x n minus r, hr. Now remember the first term has gone, the part where r is 0, that's gone. From r equals to 1 up to n, as in I'm starting here, going forward. This one here, going forward. This term here, going forward. Okay, but this now, I divide it by h. And essentially, if I divide this by h, it's the sum of r equals to 1 up to n of n r x n minus r h r minus 1. Because I've divided it by h now. So the limit, right? The limit as h tends to 0 of this expression, you can see that if h becomes really, really small, when you raise it to a power, and obviously r is a real number, that is positive, it goes from, it's actually greater than, it's 1 and above. So as it becomes, as it tends towards 0, these terms become very small. Yeah, exactly. So starting with r equals to 1, this is just 1 minus 1 is 0. H to the power of 0 is just 1. So in fact, that term is not even affected by the limit. The first term, where r is 1, is not affected by the limit. But to the power h to the power of 2, h to the power of 2 minus 1, and so forth, when h is really small, it makes this number really, really small, even more, and it makes the whole term really small, such that they disappear. They don't add anything significant to the result. So when it becomes really, really small, close to 0, so that is just 0, except for the first term where r equals to 1, because when r is 1 here, h to the power of 0 is just 1. So h becoming really small does not affect when r is 1, which is this term, which in fact is the answer. So the limit dy by dx becomes n choose 1 x n minus 1, which is just n x n minus 1. Now, what is this? If I start with a function y equals to xn, dy by dx is n xn minus 1. What have I done? I have dropped this power down here, and I've decreased this by 1. And this is always true. Okay, this is always true. Which is why now we can just drop a power and decrease the power by 1 whenever we're doing a differential of a polynomial, because we have proved it here. So I will stop this video now, and I will continue with the differentiation topic and talking about the chain